Every time you open your favorite game or app, you are greeted by a screen full of personal details. You see your unique username, your current level, and exactly how many coins you have left to spend. Behind that sleek design, your device has to track all of those distinct, constantly changing details at the same time, without ever mixing them up. If we peel back the polished menus and graphics, we find that the heavy lifting is actually being done by lines of raw code running quietly in the background. That code manages your information using what programmers call a variable. You can think of a variable as a labeled parking spot in your computer's memory, built for the sole purpose of holding on to one specific piece of information. Without these designated memory boxes, an app would have no way to remember who you are or what you've achieved. They are the essential storage units that make software work. The Java programming language is strict about how it organizes these boxes. Before it allows you to build a storage container, Java demands to know exactly what kind of information you plan to put inside it. Programmers call these rules data types. They act like a blueprint, defining the exact shape, size, and allowable contents of every single container, so nothing gets misplaced. The string blueprint holds plain text, like a name. For counting, Java uses an int, reserved for whole numbers without decimals. Java prevents putting the wrong item in the wrong box. If you shove text into a number container, the system rejects it immediately. This sorting process prevents your computer from accidentally trying to do math with a word. It ensures your data behaves exactly as you expect. To build a complete digital profile, we need a few more specialized containers in our toolkit to handle different shapes of data. Java offers the double for decimal precision. The char is a small box storing one single letter. The Boolean acts like a switch, toggling true or false. Lined up, these structured boxes translate directly into raw Java code. What might look like intimidating syntax is really just an organized inventory list, telling the computer exactly what space to set aside. But software is rarely stationary. To do anything useful, these storage boxes have to interact with one another and change as the program runs. Take a typical online checkout. When you buy an item, the app looks at the decimal value in the price container and subtracts it from your account balance container. The system reads the data, does the math, and updates the balance box with the new result. This exact exchange of information is happening millions of times a second inside mobile games, in banking apps, and search engines. These variables provide the mechanism for an application to perform calculations, adapt to user input, and make logic-based decisions in real time. When you break it down, variables are simply storage boxes, and data types are the rules dictating what goes inside them. By organizing your information into strings, ints, doubles, chars, and booleans, you have the blueprint to build the logic for almost any program. You now understand the conceptual foundation of how Java manages memory. Your next step is learning the exact keystrokes required to type these boxes into existence, a process known as declaration and initialization. By learning how to create and manage variables, you can now define exactly how your own programs store, retrieve, and process information. Imagine walking into a massive, highly automated storage warehouse. All around you, robotic arms are perfectly sorting items of every imaginable shape and size. To run a facility like this, you have to be smart about space. You wouldn't waste an entire shipping crate to store a single piece of paper, and you certainly couldn't cram a car into a shoebox. Everything works smoothly because the system matches the exact size of the container to the specific item being stored. By separating containers into distinct, specialized categories, the warehouse runs efficiently, never wasting an inch of shelf space. When you write a computer program, Java manages your computer's memory using that exact same warehouse logic. To keep things organized, Java splits all data into two main categories: primitive data types and non-primitive data types. If you want to build applications that are stable and fast, you need to know which container fits your data. Choosing a data type is how you give the computer precise instructions on how much space to reserve for each piece of information. Let's start with the standard issue boxes provided by our warehouse. In Java, we call these primitives. Primitives have very strict rules. They are quick for the computer to access, they come in rigidly fixed sizes, and they can only hold one simple value at a time. This grid shows the complete set of primitive data types. Java provides exactly 8 of these standard boxes for you to use.
To store numbers, you'd pick a box like an int for a whole number, like a person's age. If you need decimal points, say for a bank balance of $99.50, you would use a double. For non-number data, you use a char to hold a single keyboard character, like a letter grade. And if you just need a simple true or false switch, you use a Boolean. Because Java built these 8 specific boxes into its core system, the computer knows exactly how much memory space each one will take up before your program even starts. That predictability makes primitives the simple, reliable building blocks for all data in Java. But what happens when you need to store a complete student profile or an entire paragraph of text? You can't do that if you only have boxes designed to hold a single letter or number. For larger, more complicated information, Java lets you build custom shipping crates. These are called non-primitives. Here we see how non-primitives work. Types like strings for text, arrays for lists, and objects group together many smaller pieces of data into one connected structure. These crates do more than just hold data. A student record, for example, can actively perform a task, like calculating a GPA or printing a report. These built-in abilities are what Java calls methods. Non-primitives give you the flexibility to recreate complex, real-world items inside your code. Because primitive boxes are small and fixed in size, the computer physically stores the actual value right inside the box. However, non-primitive crates can grow quite large. If the computer had to pick up and move a massive crate of data every single time your code referenced it, the system would slow down significantly. To keep things moving, when we open a non-primitive variable box, we don't find the data itself. Instead, we find an address label, a specific coordinate pointing to where that massive crate is parked in the warehouse. Primitives hold direct values, while non-primitives hold these coordinates. This distinction is the key to how Java handles memory efficiently. Let's look at a side-by-side comparison so you can choose the right tool for the job. First, origins. Primitives are built directly into Java, while non-primitives are custom created by you, the programmer. Next, capacity. A primitive holds one simple value. A non-primitive stores collections of data and can perform tasks. Selecting the correct container helps your program run with minimal overhead, preventing the system from searching through empty space. You now have the foundation to structure and manage any data you encounter in Java. These 3 topics are the bedrock of your coding knowledge. But here is a challenge. What happens when you have a large piece of data, but you need to fit it into a smaller primitive box? We will solve that problem in the next lesson, where we cover typecasting in Java. You are making steady progress. Keep learning Java one core concept at a time. Have you ever ordered a coffee through an app on your phone? It feels incredibly effortless. You tap a few buttons, and minutes later, a hot drink is waiting for you with your name on it. But behind that simple screen, a lot has to happen perfectly. The app has to remember exactly what you typed for your name, safely calculate the financial math for your total, and instantly figure out your whole number loyalty points, all without crashing. Think of the code powering this app as a digital barista. To manage all this information smoothly behind the glass, Java uses 3 essential tools. First, we use constants to lock in strict rules. Second, we use typecasting to change the shape of our data. And third, we use the scanner class to actively listen to what you, the user, want. Writing code means safely and predictably managing the everyday flow of information back and forth between a human and a machine. Let's start with setting strict rules. Every application has certain values that must stay completely fixed while the program runs. Take something like a regional sales tax rate. That number cannot change in the middle of a transaction. If we store that tax rate in a standard variable, we run a serious risk. Because variables are literally designed to vary, a glitch or a tiny typo in our code could accidentally overwrite the tax rate to 0, wiping out our financial math. To prevent this, Java provides the final keyword. Typing final before your data type permanently locks that variable's value. Once declared final, any attempt to change it is immediately blocked. Java flags an error and refuses to run. By acting as the unbreakable laws of your application, constants make your code safe and reliable, especially for important configuration numbers that should never budge. While some data needs to be locked down, other data needs to adapt. Applications constantly move information between different sizes of digital memory containers. When moving data from a smaller container, like a whole number integer, into a larger container, like a decimal-friendly double, we call this widening casting. Because the destination space is much larger, Java handles this conversion automatically in the background. It is a safe translation. You never have to worry about data spilling over or getting lost when moving into a bigger space. But what happens if we need to go the other way? Imagine our coffee app needs to convert a highly precise total, like $4.99, into a simple whole number for loyalty points. This is known as narrowing casting, forcing a larger data type into a smaller space. The whole number 4 fits into the integer container, but the 0.99 fraction has nowhere to go. It overflows and evaporates. Because information gets destroyed, Java will not do this automatically. As a developer, you must manually type out the cast in your code, explicitly telling the computer you accept this loss of decimal precision. Typecasting gives you total control over how your data changes shape, provided you understand exactly what happens when you cut information down to size. We have our locked rules and our adaptable data, but none of that is useful if our program operates without knowing what a person actually wants to do. To hear the user, Java provides a built-in tool called the Scanner class. Think of Scanner as a listening bridge that monitors your computer's keyboard and passes those keystrokes straight into your code. To set this up, we tell Java to grab the Scanner tool from its library, sort of like bringing a specialized instrument onto a stage. Once it's there, we activate it so it can start monitoring the keyboard for activity. Once it is listening, Scanner acts like a digital sorting filter. It uses specific commands to catch exactly what it needs, grabbing a full string of text for a customer's name or capturing a whole integer for the quantity of coffees they want. Scanner lets your code wait for a person to type, reacting to specific words or numbers, allowing the program to respond to real-world events. Let's pull back and look at our digital barista, successfully processing a transaction from start to finish. First, the program uses the scanner to listen to your specific order. Next, it applies the fixed constant value to calculate the exact tax. Finally, it uses typecasting to chop off the decimals and issue your flat loyalty points. When you look under the hood, complex interactive software is essentially a combination of strict rules, adaptable data, and active listening, all working together. We have now covered the foundations of how Java stores, converts, and receives information. These building blocks prepare you for our next step, using operators to actually manipulate that data. That wraps up our complete overview of Java fundamentals. Until then, keep coding, keep learning, and keep growing.
You're playing a game, your character grabs a coin, and instantly sparks fly, and your score ticks up. Or maybe you're shopping online, you apply a promo code, and the total drops in a split second. We see these instantaneous updates all day long. But how exactly does your phone or computer know how to perform those math problems the moment you interact with the screen? Behind every sleek app interface or polished game, there is a hidden layer of simple commands constantly doing math, updating values, and making choices. To see how this works, we have to look past the pixels and step into the code itself. Think of writing a Java program like writing a sentence. The data you store, like a player's name or their high score, are your nouns. They are the subjects of your sentence. But nouns alone can't do anything. To make things happen, you need verbs. In Java, our verbs are called operators. Operators are the active mechanisms, the tiny gears that take static pieces of data and actually perform actions with them. Let's go back to that shopping app. Imagine you have a base price and you need to add sales tax to get the final bill. This shopping cart shows how we solve that. Java gives us standard arithmetic operators: addition, subtraction, multiplication, and division. When we place a plus sign between price and tax, Java combines those two values to create a brand new number. Now we have a total of 15, but we need to store it. We use the equal sign. In Java, this is an assignment operator. It tells the computer, take the number 15 on the right and assign it to the word total on the left. By using arithmetic to do the math and assignment to save the result, you have the exact tools needed to track and update any number in your software. Apps also need to make choices every single day. Think about logging into your bank. The app has to decide if it should allow access or keep the account protected. Look at this digital scale. It shows how Java uses comparison operators to check if two things match. By placing two equal signs side by side, we ask Java a strict yes or no question. Is the password the user just entered exactly identical to the password we have saved? Sometimes you need to check multiple rules. In a game, maybe you can only enter a new area if you are level 10 and you possess a specific power-up. We use logical operators for this. The double ampersand means and. Data passes through only if both requirements are met at the same time. These comparison and logical operators act like the senses of your software. They allow it to read its environment, verify facts, and prepare to take the next step. When you take those variables, your nouns, and combine them with operators, your verbs, you build an expression. Bringing price, plus, and tax together creates a complete mathematical sentence. You can string together a long expression with dozens of variables and multiple operators, but Java's job is to crunch all that data down into one single usable result. Mastering expressions gives you the basic tools to tell Java exactly how to process the information in your program. If you have a long sentence filled with multiple operators, a problem arises. How does the computer know which math problem to solve first? We can see how Java handles this right here. Just like the math classes you took in school, Java follows a standard order of operations. It will prioritize multiplication and division before it looks at addition or subtraction. If you need the addition to happen first, you just wrap it in parentheses. That overrides the default rules, forcing Java to add 10 and 5 together before multiplying that result by 2. By knowing these traffic rules, called operator precedence, you ensure your programs perform their calculations in the exact sequence you planned. This view brings us back to the apps we started with: the game, the bank, and the store. Only now we can see the expressions driving them. Every time a score increases, an account balance updates, or a shopping cart totals out, it is because one of these short lines of code executed perfectly in the background. The smooth, responsive software we use every day relies on a vast, organized collection of these simple digital sentences working in harmony. To recap, your variables hold the raw data, your operators trigger the actions, and your expressions combine the two into a complete thought. But that leaves one big question. Once your program uses a comparison operator to check a password and finds a match, how does it physically branch off to the next part of the app? That leads us to our next step. In the upcoming module, we'll move into decision-making and learn how to make your code branch off and react to different situations.